But can we make it full screen? It's better, yeah.
Let's now move to the third and last talk of this session, which is given by Barry Garraway on time-independent evolution of rings and shells in ultra-cold atoms. Please.
Thank you. And thank you very much for the invitation to come here and celebrate Victor Dodonov's 75th birthday. It's a great pleasure to come to this second meeting, especially as I came to the first meeting, and it's pleasant to have the memories confirmed. I remember all these posters here from before, from 12 years ago, was it? Amazing. Anyway, thank you. Okay, so this is the plan of the talk. I'm going to talk about rings and shells of ultra-cold atoms. This is going to become very clear what I mean by that in the first part of the talk. And this is going to be the main first part. It's an introduction to these rings and bubbles that I'm talking about, which are very often made with BoseEinstein condensates. But I will also be talking about a sort of single particle picture, non-interacting systems with this, because that's a bit easier. And then in the last part, I want to talk about the project which takes us towards guided inertial navigation. I'm not going to say too much about that. It's something that's in progress, but it's the motivation for the last two things. So one of these is what I call the propeller. So this is now going to be a specialized quantum system. It's actually harmonic oscillator in 2 dimensions, so it seems very appropriate to at least briefly mention that here. And then I'm going to talk about finally this free expansion of rings and shells, how we analyzed that problem, which is something of interest to experimentalists. Now, the workhorse behind making these shell states of condensates and also the rings in this particular case, the workhorse of this is something called radio frequency dressing, essentially using a radio frequency field and magnetic resonance to create new topologies for these atomic systems. And just in case I have to rush things at the end, these are 2 review articles that we wrote and published in 2016, 2017, which if you become interested in this, it's a good place to start because we explain it all from first principles, although I will also do that in this talk, give you the first, well, the simple explanations of how that works. But you can go to these review papers. So this one's not so easily accessible, so we put it on the archive where you can find it in 1706. Right, so that's the plan. So, before starting, I talk about another anniversary. So I moved to Sussex University from Imperial College in 1997. I'm a theorist. And at the time, they were just beginning to set up this experiment to observe BoseEinstein condensate, which actually happened a year later after I arrived. This is the local newspaper cutting, in which they celebrated making the Brighton apparently the coldest place in the universe, official as a newspaper, I should say, like with a stamp or something. And this was nice. So I'm not involved in that experiment, but I'm mentioning it because this was the environment into which I arrived, already having been exposed to quite a lot of cold atom stuff as a quantum optician. Anyway, the article goes on to say, Icemen, Malcolm, Boscher, Aidan, Arnold, this was the experimental team that succeeded to get into this low temperature. So this was the first Bose-Einstein condensate in the UK, and that's reaching its 25th anniversary. It's amazing how time flies. In 22nd of September this year, so in less than a month, we're going to mark that 25 years of BC, the first in the UK. Of course, that was something like 17th in the world at that time. Still notable, but probably after Brazil, maybe. I don't know. I'm not sure. Somebody must know where Brazil was in that sequence. Nope. Okay. So anyway, that's another anniversary that's coming up. So that was the environment and provided the background to thinking about the ring and shell problems that I'm going to talk about. Now, I can assume here that many people know about magnetic trapping. Can I assume that? So I just briefly mentioned the concept. So that this is, so for a typical magnetic trap, and our favorite atom is rubidium-87, leading to Bose-Einstein condensates. The basic principle is that you use this Zeeman splitting, which results in a change in the internal energy of the atom as a function of magnetic field. But the trick is that your magnetic field strength varies in space. That means then you have a change of energy with space, and that's how you make a magnetic trap. So, and in this talk, I will talk about radio frequency transitions, which are transitions between the Zeeman states. And here, for simplicity, I'll just keep it to the linear regime. We won't worry about all this stuff out here where it's non-linear. And the microwave transitions that I will mention later on are going between the f=1 and f=2, the hyperfine splitting state here, so which is at the microwave frequency. But in this first part, we're just talking about this radio frequency interaction, and we assume that these Zeeman states are just evenly split. And here's a very simple picture, actually not of rubidium, but of a f=1 Zeeman manifold split into the 3 sublevels. And the concept that's important for making these shells is what happens to the atom if it's moving around. So now notice this Zeeman splitting. It's not as a function of magnetic field, but as a function of space, because the strength of the magnetic field is varying linearly in space in this simple model. And so the potential is going downward for this Zeeman level MF-1 is going down here. This is MF0, this is MF+1. If the atom starts up here somewhere at this location in space, this gradient in the potential results in a force that accelerates it down here. So it goes downhill. But now I've introduced here the magnetic resonance. So there's this resonant radio frequency field at that location. It has a fixed frequency, so it's resonant at a fixed point in space. And I've marked where that point in space is here. So if the atom goes into this resonance sufficiently slowly, then there is an adiabatic transfer of the atom to this other upper Zeeman state. So effectively it follows the path of going here, and these are internal states, but they have different energies, and it comes up here, and on this state it feels a repulsive force, so it's being decelerated, it slows down, and eventually it'll, whoops, I need to go forward, eventually it'll go down back and come back to where it started, and then the process will repeat, so it's oscillating backwards and forwards here. Now I'll give you another picture of how this works, but essentially if you look at the dressed states, which you get by diagonalizing the Zeeman manifold with the magnetic resonance with the radio frequency field, you make that diagonalization, then you have essentially a potential, the dressed potential, which is a combination of this bit of bare potential here and this excited part of bare potential over here, which makes this trapping potential, and the atom is stuck in the middle here, oscillating backwards and forwards. So this is the picture that I used in the early days to try and convince experimentalists that this might work to trap atoms at a specific location. The counter argument was that it's complicated, there's a magnetic resonance there, there's no way that the atom will remain trapped, it will just go out all over the place and you can't do it. But some people were convinced by this kind of argument. The real argument that I used to myself is one based on the Landau-Zenner problem that Wolfgang Schleich was talking about yesterday. Landau-Zenner is very powerful for this kind of situation where you have crossing energy levels. And our energy levels, they don't really cross, I mean, except maybe at the origin, which is not a good place to go because the magnetic field would be zero over there. But there is a kind of crossing at this point here where you switch from one energy level to the other energy level at that point, but where if you had only a weak interaction here, you would just continue going down. And it's a crossing in time in Landau-Zenner. So if you look at the classical trajectory of the atom here, then it's, in this case, if there's no interaction, it's just accelerating down here and picking up a speed which is increasing linearly in time. Landau-Zenner says that the potential energy of the system, if you have no coupling, would just vary linearly in time. That's not strictly true for this system. If you have no interaction here, you're actually accelerating a bit faster than that. But locally, in the region of the magnetic resonance over some small distance, you have this trajectory which is going to be having an energy which changes linearly in time. So it's a reasonable model for the region of magnetic resonance to apply the Landau-Zenner model to the classical trajectory of the atom going through that magnetic resonance. Now, Landau-Zenner is wonderful. You can predict how, if an atom is, as Wolfgang said yesterday, if you have an atom up here, you can predict how much of the atom will go on this trajectory and how much will go on this trajectory. In general, it's split between those two states. Here I talk about 2 states, but you can do it with 3 states, 4, 5, or whatever as well. But the aim here is not to split it like that, but actually to get it to move pretty adiabatically. And here I draw the adiabatic energy level curves for the upper state and the lower state, obtained by diagonalizing the problem. So this is the time-dependent Hamiltonian, as Wolfgang had it yesterday. We can diagonalize it. And what we want for this trap is an adiabatic pathway, which means that we want it all to go on this output up here and not have some small amount going down here. And the magic of Landau-Zenner is that you're almost guaranteed that once you get into the right parameter regime because of the exponential behavior of the probability of being in this state. So the probability of transferring to here is an exponential of a parameter which I call big lambda, which is depending on the coupling strength, which is also the energy gap here, and also the slopes of these things. But once this parameter starts getting bigger than 1, you've basically reached the adiabatic regime, and it happens almost like a switch that you get into the adiabatic regime. It's not something where you get sort of closer and closer and closer. Well, you do, but it's quite fast experimentally. So basically, once the experimentalist gets into that regime, they're there, and they don't have to increase coupling strengths much further. So that's a nice way of looking at it. Another way of looking at it, kind of my preferred way, is just to take a magnetic trap. So here I produce a harmonic trap on 3 MF states. So these are Zeeman states where the magnetic field varies in a way to make a harmonic trap. This is very conventional setup for cold atoms. And if you introduce the magnetic resonance out here, not at the center as I had it, but out here, then you have a way of cooling atoms. So this is the absolutely standard method of evaporative cooling to get to very low temperatures that everybody knows about. But this is also my setup in a way for the shells, because now if I diagonalize this thing, for the evaporative cooling, people don't always do that. But if you diagonalize the system, you get this picture. So in the region of this interaction here, we have this avoided crossing, which is typical of diagonalization. And then the aim is to hold the atoms in these locations. So you have to have a method to move the atoms which start here, which is effectively in this location. The atoms have to be transferred over to these locations to fill the shell trap. This is a one-dimensional picture, but we will go to 3 dimensions very shortly. So there has to be a strategy for doing that. It turns out, we thought this was going to be a challenge in the beginning when this all started around about the year 2000. But it turns out that people are quite clever at finding ways to populate these locations over here. So actually the original motivation of setting this all up was to do 2D Bose-Einstein condensates on the surface of a proper spherical shell. And also to think about the properties of coherent matter wave bubbles. And we worried a lot about the loading scheme. As I mentioned, it turned out not to be so important. We worried a lot about the lifetime of these things. How long would this bubble stay alive, exist coherently? It turns out that that's not particularly a problem, even though we worried about it at the early time. We didn't worry enough maybe about gravitational compensation. I'll come back to that in a minute. And we certainly didn't think about sending these things to orbit around the planet, which is what's happened now, but I'll get to that a bit later. So as a quantum optician or somebody with a background in quantum optics, of course, we were interested in the matter waves and what would the vigna function for a bubble look like, for example. So that was a point of interest because this we've heard about Schrödinger cat states and things. Well, this is a very non-local object, in my opinion, where if you make a big bubble, you've got one side of it which has some kind of coherent relationship with the matter on the other side of the bubble. So perhaps we can get a clue about that by looking at the vigna functions. Well, these are the vigna functions, and to be honest, it gets difficult to interpret them, because this is a three-dimensional object. So the vigna functions are living in six dimensions, and you can simplify it a bit by using radius and angle, but it's still rather complicated. But note, for future reference, that there are some vigna functions which look a little bit like the vigna functions of Fock states, for those who know about those things, or number states. Vigna functions are a bit like this kind of thing. And I'll come back to that point later. So this is the classic Fock state, which is similar to this one. So I'll return to that point. So this was the proposal for the shell states, and it took a little while to catch on because I think there was a lot of concern that it wouldn't work. And I presented very much a 1D picture there, but to get it into 3D, you just have to have magnetic field and magnetic resonance making a 3D trapping surface. And eventually it was done. I have a picture somewhere which has disappeared in my reorganization. So this was the first experimental realization of this. And of course, this is done with the presence of gravity. So if you make a really big bubble trapping potential, the atoms will sit at the bottom. So you don't actually make a bubble of matter because of the effect of gravity. And this is my point, that it's important to think more about gravitational compensation. Actually, the original paper had a scheme for gravitational compensation, but it required quite large laser intensities to carry that out, and that was not favorable. So shortly after that was done, there were a lot of sort of follow-ups by people. I mentioned one in particular, maybe, which is more recent, but this was Chris Foot's idea of making multiple shell potentials just by adding more magnetic resonances. So one magnetic resonance gives me one shell potential. For complicated reasons, if I add two more magnetic resonances, so I have three in total, I can make two shell potentials. And that's what Chris Foot has done. These are his, in Oxford, UK, these are his experimental pictures. And there are many other proposals now, for example, for toroidal trapping surfaces based on the same idea. Ring traps I'll come back to later. Okay, I got things a bit out of order there. And I should mention quite quickly, after the French experiment, which was in the same lab as mentioned in Uwe's talk at the beginning of this session, but different experimental group in Paris 13 did the first experiment. Jörg Schmidtmeyer came pretty quickly in as well and used the same method, not to make shell states, but to split a BoseEinstein condensate and to put it back together again in a way that exposed fringes from the phase when it's put back together, the phase difference there. But that's not what I'm focusing on here. So I stick with the shells and things. So as we saw with the French experiment, the atoms lived at the bottom of the shell. People are still interested, and I'll come to the motivations later on, in filling a whole shell, a large shell, with atoms. And it seems then that there was an opportunity when this experiment on the International Space Station was proposed back somewhere, well, a bit before 2013. But this was an experiment to be done in space, which was done on a very fast timescale by using off-the-shelf components rather than dedicated spaceware. So, for example, they used a commercial atom chip and vacuum cell. We'll see a picture in a minute for the experiment. So this is the Cold Atom Laboratory, which is on the International Space Station right now. It's in orbit. And so you have what's called microgravity. And so not having gravity, you can make this big shell potential and hope that the atoms will fill the shell in a way that they don't on the surface of the Earth. So this was the timeline starting in 2012, and basically the original idea was to launch in 2017. It happened actually in 2018. These things always get delayed. And end of mission, maybe about 2020. Actually, it's still going on now with plans for further extension and with a collaboration with Germany, for example, which is going to extend the lifetime of the experiment by upgrading it. This was one of the advantages of having a cold atom laboratory on the International Space Station. Here it is. So it's this box over here next to the exercising machine of the astronauts. So the advantage is that this is an experiment in space, but the astronauts are trained to be able to pull this out, replace maybe a laser or something. There are components in there that they can change or upgrade, and then push it all back and the thing runs again. So it can be upgraded in a way that wouldn't be easy with, say, a satellite or a rocket or something. So this is just a close-up of that cold atom laboratory there. So these were very early images from 2019, which appeared on the archive somewhat later. And what we see here is the expansion of the bubble. So the way magnetic resonance works is if you have a low RF frequency, you're basically applying resonance to somewhere close to the center of the magnetic potential that's going out. When you increase the radio frequency, that magnetic resonance is moving outwards. And so it makes the bubble that you have move outwards as well and makes a larger and larger bubble. So what we see here is the radio frequency increasing, and we see the structure getting bigger and bigger as the region of magnetic resonance increases. And this is what we have then at 100 kilohertz. It should be showing a bubble with maybe covering, inside this red dashed line, and it doesn't look like a bubble. And so I will explain why that is shortly, but just wanted to show more results first. So this is work with quite hot bubbles over here, and you see that there's a hint of the shape of the bubble. There are some blobs here. So some of the reasons it doesn't look like a bubble are to do with the shape, which is cigar-shaped, which comes from the fact that it's a Yoffie-Pritchard trap, which is underlying the magnetic trap of this system. Also, one aspect of this is the camera angle. So the camera isn't perfectly aligned with the axes of the bubble, but even so, it looks like it's not quite working as a bubble. These are collapse images, which was perfect. That was something that I wanted to see happen, which is that once you've made your bubble, if you turn off the radio frequency, for example, there's nothing to hold the shell condensate in position. And then it actually divides into several parts. If you had F equals 1 there, then a component with one magnetic substate will explode outwards, and the other magnetic substate will go inwards, and a component can be left in the middle. So you have stuff going out, stuff imploding, a bit like the so-called Bose-nova of some years ago. And I thought this would be very interesting to study. And indeed, you do see it is very interesting in the sense that it is very complicated, but also more asymmetric than I would have liked, this thing. So what are the origins of the asymmetries? Well, this falls into my heading of things to be careful about. And one of the things to be careful about is surface variation of the trapping frequency. So the fact that we're making this bubble potential means that there is like a vibrational frequency transverse to the surface of the bubble. And there are consequences if this trapping frequency transverse to the surface is varying around the surface of the bubble. And unfortunately, this is varying around the surface of the bubble. Actually, this is more my second point here. It varies because it's an atom chip experiment. So you can think you have a bubble in space here. This is a setup for Yoffie-Pritchard trap, so it has a dominant magnetic field direction, so that's good. But because you have an atom chip here, there's an asymmetry in the fields as they come up, because the wires on the atom chip are closer to one side of the bubble than they are to the other side of the bubble. If you're just making a BEC in a trap, you don't worry too much about this asymmetry in magnetic fields and things. You don't have to. The problem here is that the bubble is big, and so it explores a large region of space, and the magnetic field gradients can vary from one value at the bottom here to another value at the top here, and this introduces an asymmetry in the trapping frequency. When you have an asymmetry in this transverse trapping frequency, there's like a ground state energy h bar omega over 2 associated with that, which means that the potential is sort of going up and down as you go around the surface of this thing. So a combination of these effects is causing the matter here to sort of collect more on one side than the other. The other point I wanted to make here was that the lifetime was not a big issue. I already mentioned this. So this is a theoretical study, in fact, that we made. So this is the Hamiltonian for a bubble system. We have kinetic energy term, dipole interaction. So this is a spin interaction here. We have the RF interaction with the magnetic dipole and gravity. And if we now take this system and diagonalize it from the point of view of the potential, we get this Hamiltonian in the dressed basis, which has the dressed potential that we want. So that this will have, for a linear variation of detuning, such as we have in this region here, this will have an approximately quadratic form in the trapping region over here. You have a modification due to gravity. That's okay. We expect that. Obviously not in space, but on Earth we have that. And interestingly, the process of diagonalizing this system from the point of view of the potential, of course, affects this kinetic component and introduces a term which is a bit like a magnetic vector potential here. And what we do to examine theoretically the loss rates is to use this as a perturbation of the dress states. So we find dress states which are eigenstates of the trapping potential here, and then calculate the matrix elements in perturbation theory of A squared and the P dot eta over there. And in fact, this ends up being an overlap of harmonic potentials with Airy functions, because the biggest coupling is between a harmonic potential here, which is coming from the diagonalization, and this sloping potential here. So we end up with those overlaps. And we did an experiment, well, I didn't do it, but the collaborators in Paris did an experiment which actually confirmed, roughly speaking, that this theory of leakage is good. And generally, to do that experiment, which tested the decay rate of the traps, we actually had to heavily degrade the dress trap in a way that it's not even very easy to see that effect. Okay, so now I mentioned a bit of the motivation for all this. So why study these matter wave bubbles? Well, collapsing them was always a point of interest. Stirring them is a point of interest, in particular from the point of view of studying vortices in the bubble topology. So the point is, it's a new topology. It's not just atoms trapped, but we make something which is now a spherical surface. And you can think of other topologies as well that can be made. And so the behavior of vortices in a different topology can be a bit different to what you expect. For example, the vortices need to be existing in pairs. So I'm going to mention that on the next slide. So there's something called the hairy ball theorem, or it's something where you talk about combing hedgehog fur or something, or combing a person's hairy head. Mine will not do for that, but if you comb this hair, you can't do it in a way where you only have one bald spot. If it's a sphere covered in hair, if you have one bald spot, you will have another bald spot. So you'll have two bald spots for the hedgehog or the human, which is reduced to a spherical ball with hair. And this is the hairy ball theorem. And what it means for vortices is that on a spherical topology, unlike the normal topologies, like a 2D Bose-Glass or something, you will have to have vortices in pairs, starting with two. And so people are interested in simulating and perhaps in the future observing this sort of thing. People are already calculating now modes of vibration of these bubbles and would like to see this experimentally verified on the International Space Station. And there have been calculations of condensation temperature by the different topologies modified on the surface of a bubble. That was a calculation by Selesnich. Chris Foot's been interested in tunneling between the bubbles, and you can probe microgravity and so on. So these are some of the motivations that are creating interest at the moment. Ring systems I'll come to a bit later, but ring systems may be of interest as models of expanding universes, for example. So what's nice here is that just by changing the radio frequency, you can expand out a ring system and make it bigger and bigger and see what happens to vortices and things in the ring system. So that's of interest too. Okay, so now I return to the problem of this asymmetric bubble, because you won't be able to do all these nice things with topology and so on if you have heavily asymmetric bubbles. Well, I've already said what the origin of that is. How can we fix it? So remember, it's all to do with the the fact that it's an atom chip experiment, so the sources of magnetic fields are all on one side of the bubble. But the good thing was that you have two antennas in the experiment on the International Space Station. One of them is an RF antenna, and the other one is a microwave antenna, because they also plan to do some clock experiments up there, and they wanted to have the microwave frequency. So we had the idea that we would use the microwave antenna to introduce a compensating potential, which is similar to the RF trapping potential, but which has an opposite sign, which can try to compensate. So this is the situation without this compensation. So this is our, at Sussex, numerical simulations of the shape. These are actually cross-sections using Grozbiewiecki equation in 3D. And we see here cross-sections through the condensates for different values of RF power, going across the two cases vertically, and RF detuning, trying to explore, where is a good parameter region, using the precise geometry that we see here of the wires and everything to figure this out. And we have the asymmetry. So then we add the microwave antenna. So the idea is that, because we have this asymmetry here, it means that the potential is too high in this region. So we try to do the opposite thing with the microwave and introduce a potential which lowers everything in this region, close to the surface of the chip in this case, and we compensate. And certainly there's still asymmetry in these cases over here, but in this particular case, you can see that this is all nicely green, uniform color, and we've achieved a reasonable compensation. And we're hoping that they will do this experiment quite soon on the International Space Station. Should have been done some time ago, but it just happened that the microwave amplifier was broken or something, and that's had to be replaced once they could get equipment back up to the space station. Okay, so now that was kind of the introduction to the whole thing. So how much time have I got left? Some time, I hope. Where's the chair? How much? 5 minutes? Sorry, 54. A bit more than 5, yeah, because I lost track of the time there. So I say a bit about the ring system now, and I'll return to the shells at the end. So this is more talking about the sort of things that I'm working on at the moment. Okay, so that was kind of the back history to all this and giving a context. So we're also interested in these ring potentials for potentially rotation sensing. Now, very good ring potentials can be made. I think the next slide shows how, so I'll come back to that. So basically, this is the work of Wolfgang Klitzing in Crete, and already back in 2017, he could make ring potentials with a BoseEinstein condensate in them, which have a diameter of 2 millimeters here. So truly huge ring systems with coherent matter all the way around this ring. A very impressive tour de force of making macroscopic quantum objects. It's small.
2 millimeters is huge.
But this is huge indeed. And the trick actually to make this, it is a tour de force of time-dependent potentials. The trick is to take the shell potential that I've already described to you and oscillate it up and down. And then the ring potential comes from the time averaging of this oscillating spherical potential, which is quite an amazing thing. And by manipulating that, you can tilt this ring and do exciting things like that. So the ring can be tilted, the condensate all goes to one side, then you can accelerate it up, and sort of whiz it up and get it flying off, and all sorts of exciting experiments. Anyway, we would like to use that kind of ring for rotation sensing, typically by setting off wave packets from one side of the ring, so not a fully filled ring, and sending them around on different trajectories, and then looking at them when they overlap each other again, either at the original location or more likely far away on the opposite side. And I have a collaboration with a different lab in Paris, sort of looking at those sorts of things. But where we got to with the simulation now is in the current project, just looking at the behavior of one wave packet. So it's clear what we do here. one wave packet, then we have the other wave packet, then we interfere them, so on. So it's part of the way through this. But already, just looking at one wave packet projected around this ring, there were some curious effects going on, which you might just see at maybe this instant. Okay, you won't see it at the back, but this wave packet, as it goes around, is kind of skidding around. It doesn't follow adiabatically the tangent of the ring. It's going too fast for that. And so there's some sort of lag effect in its orientation as it goes round. It was very interesting, and I wanted to understand that much more. And that brings me to the propeller system. And for some reason, there is something missing here. So that's one of those problems with putting it on another computer. So my student, Gwyn Wilson, has been looking at that. He's also, I just quickly mention, as I'm running out of time, he's looked at some other things, including noise in interferometry with BoseEinstein condensates and matter, and also, the effects of defects in waveguides, and what happens when a wave packet's going over some bump in one of these rings. I'm not going to go into that in detail. I just mention about this ring system, and it's a pity that the animation is missing there. Maybe there's a problem with codecs, but we can see this one. So basically, the angle of the wave packet is not matching exactly the tangent line that we expect there. So, is there a button to press? Yeah, you can move the mouse. See if, no. Okay, so we don't see. But anyway, you can take my word for it. You almost see it in the smaller picture. Yeah, it's there. So what we want to do with that is we can make some approximations. So for example, we can do a local, as it goes around the ring. Let's have the ring back. As it goes around here, we can do a local harmonic approximation, and then predict approximately the dynamics of the wave packet based on the classical trajectory and the local harmonic approximation. So this is very doable. I'm sure Victor knows all about this kind of thing. On the chemistry side of the world, Rick Heller has been doing this many years ago, also in the 70s, I think, for understanding chemical dynamics he had some analysis of wave packet dynamics, which historically I've used that quite a lot. So you can use this Gaussian wave packet approximation to analyze this and understand it, and that's a direction we're going in. But actually, what interests me is a generalization now to 2D of what I call extended Gaussian wave packet dynamics. So the extended Gaussian wave packet dynamics involves, first of all, basically you create a local basis for the wave packet as it's going around based on the harmonic approximation. But in that local basis, the ground state will go round. It's a time-varying basis, so the ground state goes around the ring. But also, as Victor mentioned on yesterday, was it Monday? It was yesterday. Also, as it goes around, Fock states are preserved. If you're in an exact Fock state and it was pure harmonic, it will still be in a Fock state by the end of the rotational motion. But this will be broken if your system is not perfectly harmonic. And if you introduce the corrections to that, that's what I call extended Gaussian wave packet dynamics. And I made a paper about that some years ago in 1 dimension. And the aim now in this work is to do this in 2 dimensions. It turned out to not be completely easy, I would say. I'm happy to discuss that at some point with someone. But anyway, we've been working on that. We wanted to test the results of the Heller wave packet dynamics in 2 dimensions, because this was a little bit new to me going to 2D. And we invented a test problem, which I think might potentially even make a paper itself now. And that's what I call this propeller. So the point was to take away the complication of going around the ring and just check a simpler problem. And the simpler problem is have a wave packet which isn't going anywhere, but it has harmonic potentials locally which are rotated. So 2 different harmonic potentials, and it starts out as a ground state, and you rotate the harmonic potentials, and then you should see, and you do see, this time lag in the way that the wave packet, which is also kind of spatially squeezed, follows or doesn't follow the potentials going around. Now, you can see that if you rotate the potentials slowly, the wave packet almost certainly will follow, and you'll get some angular momentum out of that system. But it will be going slowly. It won't be a lot of angular momentum. If you rotate it very quickly, probably nothing happens. In fact, we know nothing happens. We've done the simulations now. So there's a sweet spot where if you rotate it at just the right speed, you'll transfer plenty of angular momentum to the system. And right now we're exploring that. And these images are taken from one of these rotations of the wave packet, but I can't show the full results for various reasons at the moment. So that was one project, and I've been told I've got 2 minutes or something. So just very quickly mention the free expansions, and that was the last topic. So again, if you go back to the ring, very good ring, how can I understand if I let this ring go, what happens to it? How does it expand? And I need to quantify the fact that it probably doesn't expand very much. It's so big that if Wolfram-Klitzing makes this, if he releases the potentials, it probably just drops to the bottom of the vacuum vessel, like a stone, basically. So we want the numbers on this expansion. So this is the idea for this one, and I hope you are happy-ish to grant me the time. I went back to an idea of Jansky. Now, Jansky was around some years ago and will be known to some quantum opticians here, I'm sure. Jansky had the idea for taking coherent states in phase space and putting them along a line, in some distribution. He could make a squeeze state, for example. If he put them on a ring, he could make Fock states with coherent states just by depositing them around the ring. So this says it's an integral with a phase factor of coherent states around a ring. And that's a way of making Fock states exactly. So we want to simulate the expansion of this ring of matter. And so I thought, well, why not try putting lots of Gaussian wave packets, not in phase space, but in real space. So this is a 2D XY space here. So we put all these Gaussian wave packets. The great thing about this is we know how a Gaussian wave packet expands in time. So this is like a sum of Gaussian wave packets where we know all the time evolution and everything, and the difficulty is to add up everything. Okay. So we do the integrals. It's small here because it's a little bit complicated with some Bessel functions and hyperbolic functions and things. But the point is we get answers coming out of this analytically, and we can predict then when you will get interference fringes in the middle. So you can do the same thing with the shell. So here we have ring on the left, shell on the right. These are the analytic results for the expansion, short time. Overlapping here, we get this sort of jet feature in the middle, and a similar thing with a blob feature for the shell state. The interesting question, of course, you could say, well, how do you know it works? So we look at the fidelity of the numerical 3D wave functions to these analytic results, and basically you see here, even at the back, I hope, lots of 9. So really high fidelity results from this approximation. It's really quite magical that it works so well. And again, we chose ridiculously wide wave packets, much bigger than much fatter for the radius than you would use in real experiments, and it's still working fantastically well. So that's great. So finally then, we compare this to a Bose-Einstein condensate from a Gress-Prodiesky equation just to see how good it is. And it's actually not too bad, partly because if you have a very big ring or a very big shell for normal numbers of atoms, the gas is fairly dilute, so the effects of interactions are fairly limited. So it's all looking very positive for that analysis. Okay, I showed you that before. So the future, last 2 slides, I think. Future then is that actually now this space station experiment has motivated people to do it on Earth again, but now using, for example, drop towers in Bremen, new one in Hanover, and even in France, there's a possibility for small drop experiments there. So this is all being talked about and may happen in the future. For reference, we wrote an article which was published this year, 2023, looking at the possible future for quantum bubbles. So that's out there. And finally, then I just acknowledge the key workers on this. So Herman Sinoko did the microwave interaction thing that I talked about. Andrew Elborn was doing this free expansion that I discussed. and Gwyn Wilson was doing the propeller experiment, numerical experiment with the rotating potentials. And of course, I acknowledge Nathan, who's my contact with NASA. So thank you very much. And I look forward to a question or two if there's time. Thank you.
Unfortunately, we don't have time for questions, so you have to go to coffee break directly. But you can ask questions during the coffee break.
That's perfect. That's perfect. Yeah. Thank you.